Hi, I'm Bob. Welcome to the 5-Minute Econometrics, a program on basic econometric concepts and ideas. In past topics, we have touched on some statistics that appeared in the Stata regression result window or the Stata output. Today, we will have a summary of them. I will show you all the elements or the statistics in the Stata regression result window, their names in the Econometrics textbook, and how they are computed. Here is a typical result window or Stata output after we run an OLS regression. Let's look at the lower part of the window first. In the first column, we find the outcome or dependent variable y, which is the log wage in our example. The explanatory variables or the independent variables x are below it. They are union, age, schooling, and female in our case. The constant term or the intercept is in the last line. The second column contains the estimated coefficients or the estimates. The formula for the OLS estimator is as follows. The standard errors of the estimates are in the third column. It equals sigma hat divided by the square root of the total sum of squares of the corresponding explanatory variable times 1 minus r squared. The r squared is from the regression of this explanatory variable on all other explanatory variables. The next column is the t statistics. It equals the ratio of the estimate to its standard error. The t statistic is used to test the null hypothesis that the coefficient is 0. We compare the t statistic with the critical value to determine its significance. A large t statistic is often evidence against the null hypothesis. For example, the 5% critical value for a two-sided test with infinity degrees of freedom is 1.96. The t statistic for the variable schooling is 28.85, which is larger than 1.96. So we reject the null hypothesis and we conclude that on average, education is statistically significant or statistically significantly different from 0 at the 5% level after holding other variables in the model fixed. The next column is the p-values. The p-value is the probability of observing a t-statistic as extreme as we did if the null hypothesis is true. Therefore, a tiny p-value implies observing a t-statistic as large as we did under the null hypothesis is almost impossible. In other words, the null hypothesis is probably false. It is evidence against the null hypothesis. For example, the p-value for schooling is 0 to 4 decimal places. It implies that schooling is statistically significant at any traditional level. By contrast, the p-value for union is above 0.1, which means the null hypothesis is not rejected at even the 10% significance level. The union membership is statistically insignificant at the 10% level after controlling for the other variables. The last two columns are for the 95% confidence intervals. For the union variable, 0 is inside its 95% confidence interval. This means union membership has no statistically significant effect on wages at the 5% level against a two-sided alternative. In fact, from its p-value, we know that it is even insignificant at the 10% level. The 95% confidence intervals for other explanatory variables exclude 0, implying they are all significant at the 5% significance level. Next, let's look at the upper part of the result window. The upper left is a table for the explained sum of squares SSE, the residual sum of squares SSR, and the total sum of squares SST. I adopt the names from the textbook Introductory Econometrics, a modern approach by Professor Jeffrey Woodridge. Please watch this video for more information on SST, SSE, and SSR. We see the degrees of freedom in the next column. The degrees of freedom for the total sum of squares are n-1, where n is the number of observations. The degrees of freedom for the explained sum of squares are k, the number of explanatory variables. There are n minus k minus 1 degrees of freedom in the residual sum of squares. The next column is the ratios of the previous two columns. The number in the middle is the unbiased estimator of the error variance, the sigma squared hat. The rule mean squares error, RMSE, is sigma hat. It equals the square root of the sigma squared hat. Finally, we look at the upper right table. The first is the number of observations, n. The second is the F statistic for the overall significance of the regression. The null hypothesis is that all explanatory variables are 0. It can be proved that it is the ratio of the model mean squares to the residual mean squares. Please check out this video for the F statistics. We then see the p-value of the F statistic. In our case, the F statistic is large and its p-value is 0 to 4 decimal places. It implies that the 4 explanatory variables in the model are jointly statistically significant at any reasonable level. The following two numbers are the R-squared and the adjusted R-squared. R-squared is defined as the percentage of the sample variations in the outcome variable that can be explained by the explanatory variables. It equals the explained sum of squares divided by the total sum of squares. It is a measure of the goodness of fit. The adjusted R-squared is adjusted by the degrees of freedom and can be seen as a penalty for adding additional explanatory variables to the model. In our example, 24% of the variations in the log of wages can be explained by the 4 explanatory variables. Please click on this video for more information on R-squared. The last number is the root MSE. We have already mentioned it. We can use it to compute the standard errors of the estimates. Thank you very much for watching this video. See you soon on the next topic. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.